Okay, I think we can start. So welcome to all the participants. Thank you for being here to this new chapter of Trumpet Exchange Talks. My name is Francesco Ghini. I'm the dissemination manager of the consortium of Trumpet Consortium, which is an European initiative funded in the framework of Horizon Europe initiative. And today we have a new speaker for our series of webinar, and it's a member of the consortium. It's Dr. Zakaria Shihani, which is from SIA. Zakaria is actually deputy to the head of software safety and security lab in SIA in Paris. It's close to Paris. Yeah, very close to Paris. And so today he's going to present all the things that are related to AI, well, about the trustworthy AI. So which are the methods to tooling up this great opportunity that at the moment something so important. So please, the floor is yours.
Thank you very much. Are you all hearing me okay?
People cannot say anything, but can write in the chat. So if there is something, you can put something in the chat.
So yeah, so my microphone is working. Yes, it's okay. Perfect. So I'm going to talk about characterizing AI trustworthiness, or at least some aspects of AI trustworthiness, through not only the methods, but some tools that are based on the methods that I'm gonna talk about. But before going further, we're probably going to hear the word formal methods a lot. So maybe we should start by defining what we mean by that. So formal methods, when we talk about formal methods in the safety and security community, roughly speaking, what we mean is math-based techniques, math and logic-based techniques that are used for the specification, development, test, and verification of software and hardware. So as soon as you use math and logic to do that, to impact some aspect of the life cycle of the software or hardware, you're using formal methods. And the reason we use them is obviously because non-validated software can have very dire consequences when there's a bug that can cause a malfunction in a critical software, for example. And this is why more and more standards are calling for or even mandating the use of formal methods in the validation of software. So we're going to see two main families of formal methods. The first one is verification. So in the broad sense, what we do when we have a verification problem, we have an object to verify, which will, in our case, will be a software, a program. We're going to have a specification for that program, the desired properties that it must satisfy, the danger state that it shouldn't get into. And from these, we generate verification problems on a set of inputs, and then we give them to some tools based on formal verification. And these tools are going to give us either a certified answer, meaning that the property holds, or if it doesn't hold, some of the tools can give us counterexamples. And the good thing about this is if the tool says the property is validated, you're as sure as you can be that the property is indeed validated, as sure as we can do today with the knowledge that we have, based on math and logic again. So this is verification. The other side I'm going to talk about is property-based testing. So this is a testing framework, but that is a principled testing framework that is based on formal methods. In this case, you have a specification for a certain object you want to verify, and based on this specification, you're going to generate automatically, most often, testing inputs, and then you can check how your software behaves on these set of inputs. So these are the two main formal methods, type of usage we're gonna see in this talk. But before doing that, I'm just gonna have a brief, trip down memory lane in the formal methods history. because there is one particular moment, one particular period in the history of formal methods that I think is relevant for today's state of research in AI. And so you can have you have a paper called Social Process and Proofs of Theorems and Programs from the end of the 70s, where you could find this very provocative quote that says, "Program verification is bound to fail. We can't see how it's going to be able to affect anyone's confidence about programs." And so you might think that this provocative quote comes from like obscure, not known people, but actually, maybe some of you have at least from the computer science community, some of you probably recognize at least a few names. These are actually big names in computer science. We have the first recipient of the Turing Award. We have a Knuth Prize winner. So it's and the distinguished professor from Georgia Tech. So it's these are people that have been, I think, wrong, and history showed afterwards, as we're going to see. But before history changed, this type of controversy actually had an impact on formal methods, on the languages that the language that was used. The term formal methods or program verification became sort of attached to a stigma, not completely toxic, but still, when you for example, submit a project where you talk about formal verification, it wasn't seen as it could have been seen as a not serious project. It influenced a lot of the evolution of the field. The university courses that were given, the choices that the PhD student took when choosing their subjects, etc. This is highlighted in a very good book called Mechanizing Proof by Donald McKinsey. It's not a technical book, so if you don't have a technical background, I think you'll love reading about it. Donald McKinsey is a historian and sociologist. So he looked at the evolution of formal methods through the eyes of the community. I think it's a very interesting read. All this to say that um, for people from the AI community that know what winter AI is, we didn't reach that level of toxicity associated with the term formal methods, but it definitely had an effect. So fast forward a few years, and you have a very catastrophic failure of the Ariane 5 rocket. And the interesting point of this failure was that it could have been prevented had formal verification been used, because it was just a problem of in the floating point computations. And so this is a very seminal moment in the formal methods evolution, because it's the first example of a large-scale usage of one of the formal methods called abstract interpretation. We'll look at very surfacially at abstract interpretation afterwards. And so it's a very important part of our history, and it's also a very good motivation for students to give them a sense of how important it is to actually verify your programs and ask yourselves questions about the safety and the properties that you want your programs to hold, and how to arrive at the verification of these properties, or the testing of these properties. So all this to say, we have come a long way. And why I'm talking about this right now, because today formal methods is an integral part of a lot of critical software usages in the industrial world. We worked as a community very hard to achieve a high level of maturity on tools that are used for the verification and the testing of software. But today, with the advent of AI, all these tools that we made, that we spent decades on ameliorating, are targeted at human written code, like C code, for example. When you deal with machine learning, these tools are not that well suited. So what we do now, well, we're not completely back to square one, but we're at the moment in history where we were before. This is why I gave a little, a trip down memory lane to see that even if today applying formal methods on machine learning is hard. That level of difficulty was also present before. So, for example, if you take the one type of tools called stat solvers, today they can solve problems involving tens of thousands of variables and millions of constraints. But before, it was like at the first solver, the first stat solvers weren't that efficient. Absolutely not. We had to invent a lot of clever algorithms and heuristics to make them scale to industrial problems. But it wasn't the case at first. And so we were noticing the same sort of trend of, coming up with a tool to handle formal methods on machine learning that is not very, that doesn't scale well. And then year after year, noticing this tool evolving and becoming more and more efficient. So here, for example, I'm taking the example of Roliplex that became Marabout afterwards, because it's probably the first that was applied to the verification of neural networks. But you can notice the same trend in increased efficiency with almost all the tools that are out there, and there are a lot of them. And I'm going to talk about our tool for a little bit, but there are other tools as well. So another thing to say is that we are evolving much faster, probably because we don't have the same. We're not starting from zero. We have a lot of accumulated theoretical knowledge that we can build upon, and so you can see that this in the effervescence that's going on right now. There are a lot of workshops and events that are centered around the safety of machine learning and AI in general, and some of them are specifically tailored to formal methods. In addition, of course, to tracks in formal methods venues that have artificial intelligence specialized tracks. So basically, if you work in this, there's a lot of places you can publish your work. So now that that's done, I'm going to talk about very global view of the discipline of applying formal methods. So validation use of formal methods is a three players game. So on the one side, you have the object to verify, the software, which, for example, an industrial partner will bring us. And on the other side, you have the methods and tools. So this is the things that we develop. And in the middle, in the interaction, we have the properties to verify. And this, from experience, is where 80% of the interactions take place, because the partners that come have an idea of what they want to verify, the specification that they want to verify. But that specification is written in human language, so it's not immediately graspable by a computer tool. You have to formally express it so that a prover based on logic and math can understand it and deal with it. And so there's a lot of work that's dedicated to taking this high-level property or specification and then bring it closer and closer to what a machine can understand. So let's look at the type of properties that you find in machine learning today. So you have two main families of properties. The first one is which is formally specifiable. So this happens, for example, in control and command neural networks, for example, where the inputs are have a sense, a semantic directly attached to them and related to the domain of application. So, for example, here you have a machine learning tool that deals with the air collision avoidance system. So you have basically the goal is to embed it into a plane, and then the plane gets inputs based on the velocity of the plane and intruders coming into the airspace of that plane, the distance between the own chip and the intruder, the angle of approach, etc. So physical property, actually physical properties. And because these are physical properties, you can immediately describe safety specification. For example, if you have a description of a specification that says, I want my model, if an intruder is near and approaching from the left, I want the network to say, advise strong right, meaning turn right. So this is immediately translatable into a formal specification in math and logic, because We know what near is, it's a distance. We know what approaching is, it's a speed. We know what the left is, it's the angle of approach. So you can actually describe this. So this is the first family of properties. And this one is the easy case because you can describe what you mean with what you have, right? Um, the other type of properties is the not directly specifiable. And these are usually high dimensional data, images or sounds. And the problem with these is that they take the form of a collection of small inputs, and the meaning of each small input is not directly related to what you mean. So here, for example, what you get in an image is small pixels, but each pixel doesn't have a meaning on its own. It's like one molecule of water isn't wet. The wetness is an emergent property of a collection of molecules of water. So it's the same with an image. The bird is an emergent concept from a collection of pixels. The problem is, of course, the computer has only access to the pixels. And so with this type of inputs, for example, you cannot describe a property that says if the car sees a pedestrian, then it should stop, because a pedestrian is an emergent property or an emergent concept of a collection of pixels. But still, you can do some verification on this, particularly when you talk about the connections between, or the distance between two inputs. So for example, if you have an input, how long do you have to go from that input to change the classification, for example? And this is usually used in the um, testing of robustness to adversarial examples, for example. So the way we use this to try to explain, on the high level, machine learning, you have distribution. What you do with that distribution is you pick relevant inputs, and then you train your neural network, for example. Let's go with neural networks on these inputs. And what you want to achieve is um, a familiarity of your neural network with as much of the distribution as possible. So it goes from these little inputs that you chose to represent the distribution, and what you want it to do is to work well on as big of the portion of the distribution as possible. And what you don't want to is that it works well only on the inputs that you gave it. It overfits on these inputs, and it doesn't work well for the other for the rest of the distribution. So for this, you can first check how the network behaves on the neighborhood of certain selected representative data points, either by formally verifying all the inputs or by testing a lot. So you pick examples from that neighborhood and you test them. The good thing about test is that you don't have a guarantee on the whole range, but you can pick a bigger range and uncover more space. Whereas in verification, it's costly, but you're sure when you give it a range, you're sure to cover all the range. So this can detect when your network is overfitting. But if the test passes, it doesn't necessarily mean that your network is generalizing to the whole distribution. It's just a way of debugging, detecting early on the problems that you can have in a model. You can also use that same principle, picking representative data and generating test inputs from these selected inputs based on the properties that you want your model to be robust against. For example, if you want your model to be robust against blur, you can generate blurred images from selected inputs. If you wanted to be resistant to different lighting conditions, you can either darken or lighten inputs to generate other inputs. And the same principle holds. What you want to do is check how, if it's overfitting on the selected inputs that you give it. You can also combine the methods you can generate and then verify the around the inputs, etc. Right. So this is general view on the properties and how to verify them. Now the tools that we have. I'm going to talk more about our team, even if, of course, as I said, for verification, for example, you have many tools that exist outside of CEA, obviously. So CEA is an institute of research that is the goal of CEA is to be a frontier between academia and industry. So we're connected to the both communities, and we try to have tools that are as industry relevant as possible. So we bring them to a level of maturity that makes them usable in an industrial setting. And our research is organized into five main pillars, which is verification, test, a platform to collect the tools that are related to characterization, characterization of trustworthiness. We also deal with symbolic AI and with explainability and uncertainty. So I'm going to briefly go through all of these. First one is PIRAT, for Python Reachability Assessment Tool. So this is a tool based on abstract interpretation, the properties that we talked about before. And what we do with this tool, roughly speaking, is to, when I talk about the range around inputs before, what we do is encode that range of inputs and then propagate that range over all layers of the neural network. And at the end, if the over approximation is in a safe state, we know that the actual behavior is also in a safe state because the actual behavior is inside that over approximation. If it's outside, then it raises an alarm, but we don't know if it's half and half. We don't know which half it is because the outside can come from unprecision or lack of precision of the analysis. If it's completely outside, then same principle holds. Because the real program is inside that over approximation. If the whole over approximation is in an unsafe state, then we know that the program is also in an unsafe state. And so we used it with a partner from the energy sector that has so their goal is to have floating platforms to drill wells. So instead of having big concrete platforms, they have large ships, let's say, that position themselves over wells and then anchor themselves to not move, obviously, because if you're drilling a well of oil, you don't want to move. You want to be as stable as possible. So they put chains, anchor chains in the water, and these chains are enormous. Like the one link of a chain is the size of bigger than a human being, and they can go for like more than a kilometer. And so what can happen is a malfunction in the chains that is far away from the ship. And when that happens, because the chain is so solid, so thick and heavy, you don't necessarily see that there's a problem. And it's only when there's a rough weather or a storm or something that you realize that you have a problem because your boat is no longer anchored properly. And so what usual people that do this do is have tension detectors on the chains to see if there's less tension, which can indicate a failure. But the problem with this is that any sensor that is close to salt water, obviously salt water is extremely corrosive, so it doesn't last more than a year. And so they came up with another way of detecting failures in anchor chains, which are the movement of the boat. So they take movement of the boats that are detectable by satellites. So here you have sway, yaw, and surge. And based on these, and they take these information into long period of time, and based on these, they can detect. They give that to a neural network, and the neural network says that there is a problem in one of the four groups of the anchor chains. So the chains are organized into four groups that are perpendicular. And so they came to us with this model, and we were able to verify some safety properties that I cannot talk about, but other stability properties because of the sensors, the GPS sensors have an error range. The precision of the sensor is not absolutely perfect. And so what we were able to do is take into account this precision gap and encode it into PIRAT, and then verify the neural network that they had on this imprecision. So basically what we were able to characterize is that the model was solid or stable in that range of imprecision of the sensors. So this is one example of the usages of formal verification. Right, so we move to testing. Oh yeah, before going there, so this is just a little summary. Yeah, it's used in formal verification of neural networks. It's based on abstract interpretation, conservative over approximation, all the things that I said. You can check the website on this little QR code. And Pirate came third into the international verification of neural network competition of this year. We hope to do better next year, but it's already a good result that we had. So Amos is for AI metamorphism observing software, is a test generating tool based on metamorphism. So metamorphic testing, in a nutshell, is you take a relation that relates to inputs and a relation that relates the outputs of these inputs, and you generate inputs based on the relation on the inputs, and you check that the relation on the outputs stands. So why is this useful? Usually the test, you can have a large table of inputs and the corresponding outputs that you want, and you just call your system with these inputs and check that the outputs match. The problem is sometimes you don't have this oracle, you don't have an expected output. So what metamorphism allows you to do is, for example, the usual example on metamorphism is you have an undirected graph, and you have a software that gives you the length of the shortest point between 2 points. And so you call that software with A and B. You don't know the answer, so you cannot check the answer on that call. But you know that if you call it with B and A, B to A, then it should give you the same result, right? Because it's an acyclic graph, and so the distance between the 2 points is the same whether you start from A to B or from B to A. So here the relation on the inputs is the symmetry, and the relation on the output is the equivalence. And so you use this to generate as many test points as possible, and it can detect problems. But if everything succeeds, as I said before, it doesn't mean that there is no problems, obviously. Yeah, so this is what I said. You take inputs, you have transformations on the inputs, transformations and outputs, and you compare the two. And so we use this with ACAS, again, the air collision avoidance system. So you take your domain of application and you ask yourselves, what are the things, what are the relations that I can extract from my usage to test my model. And so, for example, if you take ACAS, you know that you have answers depending on the angle of approach. And so what you should have is that if you have an answer an answer A on an intruder coming from the left, you should have the symmetrical answer if the intruder is coming from the right. And so you can generate tests based on this symmetry in the input that implies symmetry on the output. So we did that, and we were able to check stability for this. We also had another partnership with an industrial car manufacturer that had welding belts in the factory, where you had I think it's belt, like yeah, I think so. Yeah, it's a belt where you have the pieces, and then the pieces come to certain places where they get welded together, and then the belt moves again and stops in front of camera. The camera takes a snapshot, and an expert checks the welding point to see if there's a problem in the welding joining of the two pieces. And so we interacted with this partner for a while to try to find the properties that the model should be robust to. And from this interaction, they told us that one, this whole setting is used at different times of the day, so you have different lighting conditions. So the model should be robust to different lighting conditions, and that the belt doesn't stop exactly at the same spot every time. So it sometimes stops a little further, sometimes it stops a little before the camera, and so the focus on the image is not always the same. And so the model also had to be solid to stable with regards to blurring of the image. So using Amos, we generated Amos can handle a lot of transformations. So we generated transformations based on this, and we were able to compare different models that the industrial partner had. So these are just example of how to use the tool. It is freely available for teaching purposes. If you're in charge of an AI course and you want to give your students a sense of the importance of taking into consideration the safety aspect of their models, then get in touch with us and we can see how we can work together to put Amos into their hands so they can. It's very easy to use. So even for students of level of Masters 1, that should be fine. Right. Oh, and the QR code leads you to a demo that should be working even if all of you get on it at the same time. But we're working on a better server, on a more efficient server to put the demo on it. Now the platform, Kaiser, which stands for characterizing AI safety and robustness. The goal of Kaiser, it's work in progress, obviously, but it exists and it's already integrates many plugins, many tools. But the faraway goal that we want is to have it take into input a model and a specification, which will be the use case, and then encode the model and the specification, and generate from that large formal specification smaller and smaller bits of the proof obligations, and then based on the form of these proof obligations and the the activation functions, the hyperparameter of the model, based on that and on previous runs, it can dispatch the proof obligations to a set of tools. So for example, it can say, based on my experience, I know that Marabout is very good with small perturbation on convolutional layers, for example, and this model has a lot of convolutional layers, so maybe Marabout is best for this sub-property. And then what we wanted to do also is aggregate the results and generate visualization and some stats to be used in an assurance case, for example. So Kaiser right now it's open source, so you can. We're already in discussion with tool providers. Some of the tools are already integrated into the platform. We can handle SVM, so support vector machines. We can handle XGBoost models, and we can handle neural networks. But we're it's not limited to neural networks. Kaiser is built to be not only applicable to many models, but also to ensemble of models. So for example, if we had an industrial partner who had an ensemble model where they gave the input to a neural network and then the output of the neural network to an SVM. So Kaiser would be able to give the properties that deal with the neural network to neural network specialized tools, and the parts that deal with the SVMs to SVM specialized tools, and then merge the two. So this is the Kaiser platform. You can also visit the website if you like, and it's open source. So if you want to test it or to include one of your tools in it, then get in touch with us, and we'll be happy to discuss. Now for symbolic AI, I'm going to move quickly on it. I think what I will say is that so the Colibri and Co, it's called Colibri and Co because it's a suit. There's the Colibri tool that stands for Constraint Library, which is a constraint solver, so symbolic AI, that gave rise to two other tools. And one of them is Colibrix for certified solver. And the principle of Colibrix is rather elegant. It's that we encode the different bits of a solver into a proof platform called Y3, for those who want it, who knows it. And this platform allows you to verify code using a set of solvers. But more importantly, once you have the proof, you can extract from the proof a C code that implements what you're proving. So what we do is prove in Y3 the different domains, the propagations, the labeling methods, the reduced products between the different domains of the solver, and then once that's proven, you can extract a solver in C. And the reason we do this is because we have partners that have that need solvers to be embedded into constrained environments, and so the C code is good for that. It's closer to the machine. And another thing that's good with Colibrix is that the pun with bricks is chosen on purpose. It's because you can also, for industrial partner, for example, who only uses floating points, that isn't interested in integers or bit vectors or real numbers or uninterpreted functions, etc. They can pick the type of data that they need, for example, floating points, and then they take the domains, the propagations, labeling methods of floating points, and then only extract the solver that is specialized in floating points, which will be a smaller solver. So it allows Colibrix allows the industrial partner to tailor the generated solver on its particular needs. So this is one thing why this is one reason why we worked on this type of architecture. And Colibri is a well-established tool. It's also a winner of the SMT competitions, satisfiability modulo theory competition since 2017 on certain tracks, especially very, very good on floating points. And it serves as an essential brick of other tools such as Framassé for the C code, which is a platform, open source platform for the verification of C code, and Gatel, which is a tool for the verification of Lust programs, synchronous programs. All right, and you can also visit the website on the QR code. Now, for the last part, we're going to talk about particle, and particle is, so all the rest that I talked about was focused on formal methods. Particle is more AI. So what we want to do with particle is, particle stands for part identification with confidence measures using unsupervised learning. And what we wanted with particle is to have a way to detect recurrent parts in a model. And what we wanted was to not need to access the model. So we were able to take a backbone that's pre-trained and not fine-tune it and not touch it. We can basically take it as a black box. Take that neural network, that model, have access to the second to last layer. So only not exactly the classification layer, but just before. So remove the classification layer and plug just before it, and then plug different detectors on different parts of the inputs. And then train these detectors to detect different parts of the inputs in an unsupervised way. So we don't tell them, for example, when you take a bird, we don't tell them this is a head, these are the feet, and this is the tail, etc. We just give the model a bunch of inputs of birds, and then the different detectors will converge to the different parts. And we want certain properties with particule. The first one is locality, meaning we wanted to focus on something, obviously, on the object. So you see that the first one isn't focusing on anything. We want unicity, so we want the different detectors we want only one part per detector. We don't want multiple detectors to focus on the same part because it's useless. And so we add this. We enforce the property of unicity. And each detector only focuses on one, and separate from the others. And we also want it to be clustered because for us right now, the objects that we apply particle on are contiguous. So we need the different parts to be close with each other. Of course, if you apply particle to a type of object that is composed of separate, like a fleet of drone, for example, you have to change the clustering property. And the way we enforce these properties is in the losses. So we encode these properties in the function, in loss functions, and then train the detectors on these using these loss functions. You can read the paper afterwards that gives you all the math details of how we do it. And so here you have a result where each column is a detector, and you can see, for example, that the second detector is focusing on the under part of a car. The fourth detector is focusing on the headlights. But the crucial point is the detectors don't know what they're focusing on. So you need an extra step of human definition, a human that comes, looks at the detectors and says, all right, this one seems to be focusing on the headlights, this one seems to be focusing on the windows, etc. The good point about this is, unlike data annotation, where you pay someone to look at each picture, each input, and then say that this is the headlights, this is the immatriculation, this is the windows, these are, etc. The human only needs to look at some examples of what the detector sees. So, for example, 10 pictures, and then just using these pictures, for example, I can say that this one is focusing on the headlights. So I don't have to look at all the input set to manually point on the different parts. So it can also a particle can also be used for annotation purposes. And the other crucial feature of a particle is the confidence part, the confidence measure. So it not only gives you the part, but it also gives you the confidence with which it thinks that the part is there. So, for example, here you have the detector of what seems to be the lower body, upper feet, and this one is the confidence of this detector drastically falls when the feet are underwater, because here the feet are not visible at all. And so, what you can do with this confidence measure is, So sorry, before going to that, I talked about the using particle for annotation purposes. What you can use it for also is for case-based reasoning. So, for example, you take the high-dimensional input with the features that are abstract and encoded into the pixels, and you first step of generating the different parts, and then you detect the different attributes of the parts, for example, the color and the shape. And then for the decision process, the decision-making process, you have a transparent, I don't know, decision tree, for example, a transparent AI model. So you can use a particle as a first step in the case-based reasoning framework. But we can also use it, because we have the confidence measures, as an out-of-distribution detection mechanism. So, for example, what we do is you take the whole confidence measures, aggregate them, and then that gives you the normality of what the input distribution should be. And then each time you veer out of that normality, then you may be confronted to an out of distribution, an input that is not in the distribution that the model is used to know. So, for example, if you give it an image, if you train it on birds, and you give it an image of a car, then none of the detectors of any parts of the bird should find, birds, except maybe the eye, because the eye could look like a wheel of a car, for example, because it's circular and it's black. But still, all the other detectors will not be detecting. And so you take these confidence measures together, and it can give you a score of out of distributionness. And so we wrote a paper with Thales on this, and we compared code, which stands for contextualized out of distribution detection, that is based on particle. And you can see that particle is the most stable one with regards to certain perturbation. That I'm not going to go into the details of this, but you can read the paper. But basically, what we did is to be able to measure how far away, or to compare the different detection mechanism of out of distribution. What we did was we took in inputs and we applied controlled perturbations to actually measure the distance from the original image, to be able to compare the comparable. Basically, we didn't just take models that are trained on birds and gave them cars. We did that, but we also wanted to have a measurable distance. So we used perturbations. Right. So to summarize on particle, it's pluggable, so it can be added to an existing backbone without having access to it. It's a fraction of the size. It's really like surface size on the big model. It's frugal in the sense of it doesn't need a lot of inputs to be able to converge on different paths. And it converges very quickly. And we also have, related to this, a library for case-based reasoning called Cabernet. That's just coming into shape. So it soon will be open sourced, and you can use it for if you have courses in the university that deals with explainable AI. You can use Cabernet. So get in touch with us, and we can see what we can help with, obviously for free, since it's open source. Right. So I think I'm going to finish on this. To summarize, we deal with a lot of ways to characterize the trustworthiness of AI. Not all of them, obviously. But we have a very dynamic team of both, experienced researchers and students, and we're always hiring. So if you're looking to work on trustworthy AI, get in touch with us, and we'll be happy to discuss and have partnerships. And that's it for me.
Thank you very much, Zakaria, for your intervention, for your talks. So now is the moment for some questions. So if you want just to have a questions, please ask in your dashboard, and I'm going to enable your microphone, or you can also put in the chat. So maybe while we are waiting, I just ask you something that Zakaria, I'm coming from another field, so I'm a molecular biologist that behave as a communication manager. So you showed a lot of example in some very industrial sector. Have you have any expertise related to pharma company that use these tools for implementing their activity?
So we have on the medical sector, you mean?
Yeah, the pharma, the medical one is maybe more or less to hospital. The pharma is just related, to all
Yeah, so right now we don't have partners that come from the medical sector. We have dealt with open source datasets that come from that deal with, for example, detection of cancerous cells, but we haven't had actual partners that use AI in the medical sector. We have a partnership with some of our colleagues. So when I say we, I mean the team. CA does work with the medical sector, just not our team yet. We had some contacts with a company that does exoskeletons for tetraplegic patients with electrodes probably, and that replace the communication between the limbs and the brain, and so it's called Kinetech for those who know it, based in Grenoble. And we are in discussion with them to see how Pirate can be used to test the stability of their AI models within the error gaps that I talked about. So the same principle as the one I talked about with the technique, the energy partner, and also particle to have a decision procedure that's more maybe more transparent. So we're in discussions, but right now we haven't had. Well, we didn't move as far as we want to in the medical sector.
So, if I understood correctly, these tools could be also suitable for the images analysis of, for example, cell motility or images that are coming from analysis of tissues, of organic tissues.
Yeah. Yeah, absolutely. So in the case of Trumpet, this is where we want to apply, pirates and Amos on. So right now we're at the beginning of Trumpet, so we don't have the actual models finalized yet. But this is the participation that we have in Trumpet is in the validation of the models that will come up with Trumpet, or before the models come off of Trumpet, obviously.
Thank you. So if there are any questions. Okay, I cannot see anyone, so the possibilities are just raising your hands up and I will enable you, or putting your question. Yeah, there is a question on
and the goal of
chat.
seeing safety permeating our future. When we say safely, we assume we have the fear of being unsafe as well. If I'm making sense, could you explain this a bit in brief? So one way of being unsafe is, for example, if I take the example of the partners that we have that deals with drilling oil, being unsafe is, for example, not being anchored properly and then maybe moving away from the oil well, and then have an oil spill, for example. I don't know if that answers the question, but yeah, we have a fear of being unsafe. Obviously, we have a fear of a plane not detecting an intruder. We have a fear of the image detection in cancer cells not detecting the cancer at the right time, etc.
Okay. So I saw the answer. So thank you very much to all the attendees of this webinar, and so just to close this moment, thank you, Zakaria, for your great lessons. And yeah, for sure, this is the second appointment. We are going to create a new calendar for the new year in 2024. So please again follow our website, trumpetproject.eu. That have all the information and update about our activity of the consortiums, and so also the scientific publication. So thank you again very much, and let's see you to the next event.
Thank you all. Bye-bye.
Bye-bye.
Thanks.